Hi, for this video, we're going to discuss three types of techniques or theorems that can help us in solving complicated circuits. We have here Thevenin's theorem, Norton's theorem, and source conversion. I have decided to make one video out of these three topics because they are somewhat related. Okay, so once we know Thevenin's theorem, we can easily understand Norton's theorem and as well as source conversion. So in this type of methods, we are usually converting the original network to match simpler equivalent circuit for rapid calculation of different quantities. Okay, so these methods can be applied to simple as well as complicated networks. So in these methods or in this theorems, we are going to redraw. Okay, so we're going to convert or redraw the original circuit into a more simpler one. So let us start with the Thevenin's theorem. So this was named after Leon Charles Thevenin, so who formulated this theorem. So it says here it provides a mathematical technique for replacing a given network as viewed from two output terminals. Okay, so any complicated network made up of two or more sources or made up of two or more resistances, we can actually simplify it into a single voltage source with a series resistance. Okay, so it makes the solution of complicated networks quite quick and easy. So for Thevenin's theorem, it's like we will be having this, for example, this circuit here. Okay, so this circuit composed of a single voltage source with three resistances. So if we're going to get the Thevenin's equivalent circuit at points A and B, for example, so the Thevenin voltage is the open circuit voltage at terminals A and B, so we call that Thevenin's voltage. Or some other books, they write that as VTH for the Thevenin's voltage, or in some other references they write that as ETH. Okay, so that means we have a single voltage source, so this will be your VTH, this will be your ETH, in series with a specific resistance. So we call this resistance usually as RTH, the equivalent resistance. So instead of having a single voltage source with three resistors here, we can actually simplify that in a single source with a series resistance. Okay, so how are we going to do that? So suppose it is required to find current flowing through the load resistance RL. So what are we going to do? So this is our load resistance RL. Okay, so we are trying to, actually you can solve this type of problem using the previous techniques that we have already discussed, using the Kirchhoff's laws, using the mesh analysis, using the nodal analysis. And this is the approach when we're going to make use of the Thevenin's theorem. So suppose it is required to find current flowing through our load resistance RL. So what are we going to do? The first thing to do, class, is we have to remove this RL. So if we're going to remove this RL, looking at this second figure here, removing RL from the circuit terminals A and B and redrawing the circuit. So technically, we have observed here an open circuit terminals. Okay, so terminals A and B. So what are we going to do is we're going to compute for this open circuit voltage. So this open circuit voltage will then become our Thevenin's voltage or VTH. Okay, so we are going to calculate the open circuit voltage VOC, which appears across terminals A and B when they are open. So when we remove RL, what will be the equivalent voltage here? So if you place a voltmeter here, what will the voltmeter read? Okay, so that is called the Thevenin's voltage. So if we're going to do that, our Thevenin's voltage is, or our open circuit voltage here, is in parallel with R2. So whatever voltage across R2 here, that will be our open circuit voltage. So we notice also that our source here has an internal resistance. So the internal resistance is the small letter R. Okay, so when the source is not ideal, it contains usually of an internal resistance. So if the internal resistance is not given, we're just going to assume that as an ideal source or has a zero internal resistance. So if we wanted to solve for VTH here, we will just use voltage divider principle. Since the voltage E here will divide between these three resistors, the internal resistor R, R1, and R2. But what we are looking for is the voltage across R2, because whatever the voltage across R2 is in parallel with our open circuit here, therefore, they are just equal. So using voltage divider principle, we can determine our VTH as your source, which is E, multiplied by your R2, divided by the total resistance, which is your R, plus R1, plus R2. So we now have our VTH. Okay, so once we have already solved for our VTH, we are now going to solve for our RTH, or our Thevenin's resistance. So every time that you are solving for the Thevenin's resistance, we are removing all the sources that you have, either the voltage source or the current source. Every time you are getting the value of an equivalent resistance or a total resistance, there should be no sources involved. Okay, so therefore, if we're going to remove that, if we're going to short this one, if we're going to remove your voltage source here, what will remain is your internal resistance R, your R1, and your R2. So the Thevenin's resistance, okay, so now imagine the battery to be removed from the circuit, leaving its internal resistance behind, and redraw the circuit. Determine the equivalent resistance of the network. So this time we call that RTH. So if we're going to look through this circuit, okay, this is terminals A and B, what can you see? So what can we see here is the series combination of R1 and R2, and the series combination of this is in parallel with our R2. So therefore, we can solve for our single Thevenin's resistance, or what we call RTH. Okay, so our RTH now is equivalent to the series combination, so that is R plus R1. So they are in series, so we simply add them, and they are in parallel with R2. So this is now your RTH. So once you determine your VTH and your RTH, what do you do next? Okay, so once determined, RL, we are going to bring back the RL that we removed earlier. Okay, so RL is now connected back across the terminals A and B. So this is your terminal A and B. So we place again your RL there because we removed that earlier. And then we're going to put your VTH in series with your RTH. So this is now your new circuit. And this circuit is very easy because this is just a simple series circuit. So if you wanted to solve for the current, you can just solve the current using the formula that is your I is equivalent to VTH divided by RTH plus RL. Okay, so the VTH here and the RTH here is the same as what we have computed on the previous slides. Okay, so that is how you perform the Thevenin's theorem. So it says here any complicated circuit can be reduced to a simple series circuit having a resistor RTH in series with your VTH or your Thevenin's voltage. Okay, so to illustrate this further, let us have an example. So we have here, convert the circuit to a single source in series with a single resistor. So when you say convert the circuit to a single voltage source, okay, so every time you say single voltage source in series with a single resistor, it is also the same as saying that we are trying to Thevenize your circuit. Okay, so a single voltage source in series with a single resistor is the Thevenin's equivalent circuit. So therefore, looking at this point A and B, what will be the voltage? What will be the open circuit voltage, which is also the VTH of your circuit? So looking at A and B, it is in parallel with this branch. Okay, so whatever the voltage across this 4 ohms here, so this is your resistor, and this 10 volts here, that will be your VTH. So how are we going to do that? We have to solve first for the current flowing around this circuit here. So how do we solve the current? As you can see, you have 2 voltage sources, and they are and they are not aiding. Why? Because this is, if we follow the loop, this is positive 15 minus 10. So our source there is equivalent to positive 15 minus 10. Okay? So positive minus 10 divided by, what is our total resistance here? Our total resistance here is simply the sum of 8 and 4, because this is simply a series circuit, because this is already an open, because this circuit is already open. So no current will flow at this part of the circuit, making this a simple series circuit. So our total resistance there is simply 8 plus 4, or that is equal to 12 ohms. So we have here, your current now is equal to 5 all over 12, or this is equivalent to 0.42 amperes. Okay, now we need this current because we have to solve for the voltage across these 4 ohms. So what is the voltage across the 4 ohms resistor? So the voltage across the 4 ohms resistor is equivalent to the current, which is 0.42 amperes multiplied by 4 ohms. So your voltage across that is equivalent to 1.68 volts. Okay? So as you can see, the voltage across here at A and B is equal to the voltage across C and D. So the total voltage here, so they are summing. Why? Because this is plus and minus, this is also plus and minus. So they have the same sign. So therefore, our VTH is simply the voltage across the 4 ohm resistor, which is 1.68 plus 10. Okay? So our VTH now is equal to 11.68 volts. How about our RTH? So for our RTH, we are just going to remove the sources. So we are going to make this short circuit, and this is short circuit. So if that is already short circuit, we can see that your 8 and 4 here, looking at this portion, okay, they are in parallel with each other. Okay, so when this is shorted and this is shorted, as you can see, they are in parallel with each other. Because if you're going to look at this one, if we have a current here, one current will divide going to 4 and another current will divide going to 8, making them parallel. Therefore, our RTH is equivalent to 4 parallel 8. So 4 parallel 8 is like 4 times 8 divided by 4 plus 8. And that will give you 2.67 ohms. So we now have your RTH and we have now your VTH. We are going to convert now the circuit. So the Thevenin circuit now is equivalent to your VTH, which is equal to 11.68 volts in series with your RTH, which is 2.67 ohms. and this is your terminal A and B. So this is your VTH, and this is your RTH. This circuit here that composed of two sources and two resistors was converted or simplified into a single voltage source in series with a single resistance. So that is how you're going to do your Thevenin's theorem. Okay, so let's have another example. So it says here, apply Thevenin's theorem to calculate the current through the 4 ohm resistor of the circuit. So where is the 4 ohm resistor in your circuit? This is our 4 ohm, okay? So what are we going to do is we're going to remove that, okay? So we're going to remove that. So this is now an open circuit. So let us call this plus and minus. So let us say this is point A and B. Okay, so this is an open circuit. If we're going to redraw that, it's like, it somehow looks like this. So you have 15 plus and minus. So you have 10 here. You have 5 here. This is open. We have 6 here. Plus and minus 6 volts. Okay, and this is open. So let us call this A and B. So this is our VTH, plus, minus. Okay, so how are we going to solve for the voltage across this one? Okay, so as you can see, since this is open circuit, we have here, we can solve for the current flowing. We can solve for the current flowing in this first circuit here. So the voltage, we need the voltage across this 5 ohms. Okay, so we need the voltage across this 5 ohms. So how are you going to determine the voltage across this 5 ohms? We can make use of voltage divider. So this 15 volts here will divide between 10 and 5. So to know the voltage across 5 ohms, using voltage divider, this is simply 15 multiplied by 5 divided by 10 plus 5. So this is equivalent to 5 volts. Okay, so we now know that at this moment, at this portion, we have positive, negative 5 volts. Okay, how do we solve for VTH now? So if this is point A and this is point B, we can have a loop here, okay? So if we have a loop there, you have there positive 5, okay? You have there positive 5, and then you have minus VTH, and then we have minus 6 is equal to 0. So solving for VTH now, we have negative 1 volt. So what do we mean by negative 1 volt here, class? So the negative 1 volt here is means that the terminal B, okay, the terminal B should be positive with respect to terminal A. So that is how we mean by negative 1 there. So we are now going to solve for the RTH. How are you going to solve for the RTH? So we have to remove. So we need to remove this one. So this is short circuit, okay? And this is also short circuit, okay? So what we see here is just your 5 and 10, okay? And looking at this portion, we can see that your 5 and 10 here are in parallel with each other. So therefore, in solving for your RTH, this is equivalent to 10 parallel 5. So 10 parallel 5 is just 10 times 5 all over 10 plus 5, having our RTH equivalent to 3.33 ohms. And then we redraw the circuit. Okay, so we redraw the circuit. So the circuit here now is negative, positive, okay? So the current is like the terminals or the polarity is like this, 1 volt. It is in series with our RTH. This is 3.33 33, and this is terminal A, and this is terminal B. Okay, B is positive. B is positive because we got the negative sign there. So it should be minus plus and not plus minus. Okay, and then we're going to bring back your 4 ohms, the one that we removed earlier. So you're going to bring back your 4 ohms there. Okay, so that means we can easily solve for the current. So what is the current flowing here? So this is just a simple series circuit. And your I there is simply your source, which is equal to 1 volt, divided by the total current flowing in the circuit, because this is a series circuit. Although the question here is the current across 4 ohms, but we need to include your 3.33 because the same current flows at 3.33 and at 4 ohm resistance. So therefore, I is equivalent to 3.33 plus 4. So therefore, the current flowing across 4 ohms is equivalent to 0.136 amperes. So that is how you perform Thevenin's theorem. Okay? So you remove first your A, you remove first your 4 ohms, then the open circuit, you have to solve for the VTH there, and then you remove the sources, then you solve for the RTH, and then you combine your VTH in series with your RTH, and then you bring back the 4 ohms, and you can easily solve for the current. So as simple as that. Okay? So let's have another example. Using Thevenin's theorem, calculate the current flowing through the 4 ohm resistor. So what are we going to do now? So we have here, this is your 4 ohms. Okay, so we have to remove that. That will become an open circuit. Okay, so if we're going to redraw that, it will become like this. This is 12. This is 3. This is 6. This is open. Okay. We have 2 here. So let us call this VTH. A and B, assume. Let us assume the sign, minus and plus. So if we get a negative number, therefore we have the wrong assumption. If we got the positive number, therefore that is the correct polarity. Okay. And then we have here a current source. This is 10 amperes. Okay. So to solve for the voltage across VTH, we need to have our loop here. However, we have to know first the voltage at 6 ohms and the voltage at 2 ohms. No problem with the voltage at 2 ohms. Okay, so how do we solve for the voltage across 2 ohms? As you can see, the current source here passes directly at 2 ohms because this is already an open circuit. So therefore, no current will flow to the other part of the circuit. Therefore, the whole 10 amperes will flow across this 2 ohm resistor. So the voltage across 2 ohms is equivalent to 2 ohms times 10 amperes. We have here 20 volts. That is the voltage across the 2 ohm. And what is the polarity? So since the current will be flowing in this manner, okay, so this is plus and this is minus. So we have here plus and minus 20 volts. Okay, how about in this side? What is the voltage across 6 ohms? So we need the voltage across 6 ohms. So this circuit here is a simple series circuit because this is already open, meaning the current that will be flowing from this source will no longer move at the other part of the circuit because of the open circuit terminal here. So making this a simple series circuit. So if we wanted to solve for the voltage across the 6 ohms, we will just use a simple voltage divider principle. So that is your total voltage 12 multiplied by the value of your 6 ohms because we wanted to know the voltage drop across your 6 ohms divided by the total resistance, which is 6 plus 3. So the voltage across 6 ohms is equivalent to 12 times 6 divided by 9. So the voltage is equivalent to 8 volts. So that is equivalent to 8 volts. So what is the polarity? So the polarity is minus plus. It will flow here. So this is plus, this is minus, and we have here 8 volts. Okay? So if we're now going to have our loop here, so following the loop, we have here positive 6. We have here minus VTH. We have here minus 20 is equal to 0. Solving for VTH, this is 6 minus 20. That will give you negative 12. Again, what do we mean by the negative sign here? That means that your B here is positive with respect to point A. So we have a wrong assumption. But anyway, it's okay. All we have to do is just to reverse the polarity. So it will become negative positive instead. Okay? So we now have our VTH. So let us now solve for our RTH. How are we going to solve for our RTH? We are going to open the current source, okay? How do we remove a current source? We usually open that. And then we short your voltage source, okay? So this is opened and this is shorted. So what we can see here is the 3 ohms and 6 ohms that are in parallel with each other, okay? And then the parallel combination is in series with the 2 ohms here because we are looking at this manner. Okay, so if we look at this manner, this is in parallel. So solving for RTH, so this is 3 parallel 6, okay, and the parallel combination of 3 and 6 is series with your 2. So we have here plus 2. So 3 parallel 6 is 2 plus 2. We have your RTH, which is equivalent to 4 ohms. So we redraw. So how do we redraw again? We have your source. So if that is A and B, so therefore we have here again minus, plus, okay? Then we have your series 4 ohms, which is your RTH, okay? And then this is terminal A, this is terminal B. Okay, so positive, the B is positive with respect to A because we have a negative sign here. Okay, so therefore, we will bring back your 4 ohms. The original 4 ohms from A and B, we will bring that back in our circuit. And this is 12 volts. So, what is the current flowing across 4 ohms? It is very simple, right? Because we only have here a series circuit. So the current flows in this manner. So it should be plus and minus. Okay? So what is the current there? The current there is 12 volts. Divide by, okay, the total resistance, which is 4 plus 4. Okay? So, 4 plus 4. So this will give you 12 divided by 8, or 3 halves. Okay, so amperes. So that is your answer there. Very simple. So why it become very simple? Because we have converted your circuit with a voltage source and a current source and 1, 2, 3, 4 and 4 resistors into what? A simple circuit with one source and a single resistance. So that is how you do Thevenin's theorem. Okay? Now, let us go to, I have here a set work. So what you're going to do is you just you will just submit the answer for this set work in our school book. Okay, so let's now go to the Norton's theorem. Okay, so Norton's theorem is an alternative to Thevenin's theorem. Okay, so it says here any two-terminal active network containing voltage sources and resistance when viewed from its output terminals is equivalent to a constant current source and a parallel resistance. So for example, you have here networks with several sources, okay, one or more sources. It can either be a voltage source or a current source. What you're going to do is you short circuit that terminal. In Thevenin's, we open circuit the terminal. Okay, so in Norton's, we short circuit it. So that's the first difference. Okay, and then we're going to get the Norton's resistance. Okay, removing the sources, leaving the resistances alone, we will get the internal resistance of the circuit. So for Thevenin's, that is a voltage source in series with an internal resistance, or the Thevenin's resistance. In Norton's class, it is a short circuit current. Before it's an open circuit voltage. Now it is a short circuit current in parallel with an internal resistance, internal infinite resistance. Some books, okay, they call the short circuit current as INT to specify Norton's, okay, and the resistance are as RNT, or the Norton's resistance, okay. But this RNT here is just equivalent to your RTH. How do we solve for RTH in Thevenin's is the same thing as how are we going to solve for the equivalent resistance in the Norton's theorem, okay. So it says here, instead of a voltage source in series with the resistance, it will become a current source in parallel with an internal resistance. So the current is equal to the current which would flow in a short circuit placed across the terminals, and the parallel resistance is the resistance of the network when viewed from these open circuited terminals after all voltage and current sources have been removed and replaced by their internal resistances. So the steps in solving for RTH is the same as solving for the Norton's resistance, okay. Actually, class, this is an alternative to Thevenin's theorem, okay, whereas Thevenin's theorem reduces a two-terminal active network of linear resistances and generators to an equivalent constant voltage source and series resistance. Norton's theorem, on the other hand, replaces the network by an equivalent constant current source and a parallel resistance. So that is their main difference. Okay, so how are we going to compute? So for how are we going to solve problems or solve circuits using Norton's theorems? Okay, so let's have an example here. Determine the so let's compare. Okay, so let's make a comparison first. Determine the Thevenin and Norton equivalent circuits between terminals A and B. So let's start first with the Thevenins. So for the Thevenins, what we're going to solve for is the open circuit voltage. Okay, the open circuit voltage, which is also our VTH. So how do we solve for VTH? Since A and B is in parallel with R2, whatever voltage across R2, that will be the voltage across your VTH. So how do we solve for your VTH here? So your VTH is equivalent to, we can divide E between R1 and R2. So using voltage divider, this is equivalent to E multiplied by R2, because that is the voltage that we need. That is the resistance in parallel with the open circuit terminal. So divided by R1 plus R2. Okay? So in getting for the RTH, what do? We short circuit this. Okay, so when we short circuit this and look at the total resistance or the equivalent resistance in this direction, we can see that your RTH is simply R1 parallel R2. Okay, so if we're going to get the Thevenin's equivalent circuit for this one, this is simply a source, which is your VTH, in series with your RTH. And this is your terminals A and B. So that is your example. Okay, so this is the Thevenin's equivalent circuit for this type of problem. Now, we are also asked to get the Norton's equivalent circuit. So, what is the difference? So, for the Norton's equivalent circuit, instead of getting the open circuit here, we are going to, I will erase this first. We are going to get the short circuit current. So how do we get the short circuit current? So in getting the short circuit current, we short circuit this. Okay, we get the short circuit for that. Okay, and then as you can see, every time that your resistor has or is in parallel with a short circuit, this R2 here will be biased. Okay, so will be, sorry, not biased, will be bypassed. Because if I am the current, I would not like to pass anymore across this R2 because I have an open circuit here. So if I am the current, I will walk or I will flow directly across the open circuit. So therefore, R2 will be biased. Then I can solve for my INT or the Norton's current. Okay, so my INT is simply E divided by R1. Okay, now RNT or the Norton's resistance is the same. Okay, so we're going to remove this one, open again, and then we're going to short this. As you can see, our RNT is also R1 parallel R2. Okay? And then, we redraw. So, how do we redraw? So, when we redraw that, that is a short circuit current. So, we call this your INT in parallel with your RNT. And this is your terminal A and B. So that is the difference between the Thevenin's and the Norton's equivalent circuit. So this is in series and this is in parallel. Okay, so that is the difference. But basically, it is just the same. So instead of open circuiting the terminals that we wanted to solve, we will just make it a short circuit. Okay, so let's have an example. We have here, using Norton's theorem, find the constant current equivalent of the circuit. Okay, so what do we do? First is, we're going to short circuit this. Okay, so when we short circuit that, we do no longer bypass your 10. Why? Because we have 15 here. Okay, so a while ago, the resistor in parallel with the short circuit was bypassed, but this time it will not be bypassed because of the 15 here. So if I have a current here at point C, it will divide. It will not flow directly across the cross circuit. Not all of the current will not flow across this short circuit here because we have also a 15 ohm resistor. Okay, so we have here, we have to short A and B. We have already short circuited your A and B, and then we will be getting your equivalent resistance. Okay, so what is your equivalent resistance here? So REQ is equivalent to 15. So as you can see here, they are in parallel. So 15 parallel 10, and the parallel combination of these two is in series with your 10 ohm resistor. So we have here plus 10. Okay, so giving us our equivalent resistance equivalent to 16 ohms. So knowing the equivalent resistance now, we can now solve for our INT or the short actually not yet the short circuit current, just the total current of the circuit. So the total current of the circuit is equivalent to 100 volts. So we have zero internal resistance here. So we have an ideal voltage source having zero internal resistance. So this is simply 100 divided by 16. So 100 divided by 16, we have 6.25 amperes. Okay, so what are we trying to solve is the short circuit current. What current will flow across this terminal A and B? So what we're going to do is we're just going to uh, use current divider, okay, at point C. So at this point C, this 6.25 ampere current will divide. One will flow across your 10 ohms and one will flow across your short circuit. So therefore, if we wanted to solve for your I and T, or the short circuit current, this is equivalent to the total current multiplied by the opposite. So this is 10. So since they are inversely proportional, so we use the opposite, divided by 10 plus 15. So our INT here is equal to 2.5 amperes. Okay. So how are we going to solve now for the resistance? Okay, for our Thevenin Norton's resistance. So for our Norton's resistance, we're going to short this. And we're going to make this an open circuit. And then we're going to look at this direction. What can you see looking at this direction? So as you can see here, that is 10, okay? This 10 here is in parallel with this 10 here. So let us now solve for your RNT, Norton's resistance. This is 10 parallel 10. And the parallel combination is in series with your 15 ohms there. So 10 parallel 10 plus 15 ohms, that will give us 20 ohms. And then we just have to redraw the circuit. So this entire circuit can be replaced by a current source. Okay, so what is your current source? So that is flowing in this direction. Okay, so this is our current source. And this is equivalent to 2.5 amperes in parallel with 20 ohms resistance. And this is your point A and B. So this is our Norton's equivalent circuit. Okay, so this is the current source in parallel with the equivalent resistance, Norton's equivalent resistance. So the Norton's equivalent resistance is just the same on how we get the Thevenin's resistance in the Thevenin's theorem. Okay, so let's have another example. So it says here, apply Norton's theorem to calculate the current flowing across through the 5 ohm resistor. So what do? We remove your 5 ohms, okay, and then we make this short circuit. So if this is short circuit, this will also be bypassed. Okay, so this will also be bypassed because if you are the current and you will flow here at this junction, you want to pass through here already and not pass through the branch with a resistance, with a resistor. So therefore, 10 ohms here will be bypassed. Okay, so by removing the 5 ohms and replacing it with a short circuit, 10 ohms is also short-circuited. So we now get the equivalent resistance. So the equivalent resistance for that is equivalent to, this is 8 parallel 4. Okay, so since this is also a short circuit, you can see that your 8 here is in parallel with your 4 ohms there. And their parallel combination is in series with your 4 ohms there. Okay, so that will give us 6.67 ohms. So we can solve for the current. So what is the current? The total voltage is 20 divided by the equivalent resistance, which is 6.67 ohms. So this is equivalent to 3 amperes, approximately equal to 3 amperes. So it's 2.9999. So therefore, we can say that this is equivalent to 3 amperes. Okay? So, as you can see, getting now that at this point, so let's call that let's call this point C. Okay, let's call this point C. this is our A and B. Let us call that point. So at this point, that current divides. Okay, so that current divides, and we wanted to get the current which will flow across this terminal, across this short circuit terminal. So how do you solve for that? So our INT is equal to the total current, which is 3 amperes times, okay, since they are inversely proportional, this will become 4. So we need the current flowing across 8. So our numerator is 4, and this is 4 plus 8. So our INT is equivalent to 1 ampere. Okay? Now, how are we going to solve for the current, for the resistance? So for the resistance, we're going to replace this by an open circuit. Okay, so if this is an open circuit, open, 10 will not be bypassed. So 10 is still there. And what we're going to do is to replace this with a short circuit. And we're going to look at this manner. Okay, so looking there, what do we have is, we have here 4 parallel 4. So to solve for our NT, so we have here 4 parallel 4. So what is 4 parallel 4? 4 parallel 4, that is equivalent to 2. Okay, so this is 2. The 2 is in series with your 8. So 2 plus 8, and they are in parallel with 10. Okay, so therefore our RNT there is equivalent to 10 parallel 10, or simply 5 ohms. So in that case, we are going to redraw. We have a current source with 1 ampere in parallel with your RNT, which is 5 ohms. And then, we're going to bring back your original 5 ohms, the one that we have removed. 5 ohms here. So 1 ampere. So, your 1 ampere will divide. Okay, so your 1 ampere will divide plus minus. So that this is the direction of your current. So at this point, it will divide between this one and this one. Since they are both 5, what do we do? So the current across the 5 ohms resistor is simply half, because they will divide equally. So therefore, this is equivalent to 0.5 amperes. So that is how you perform Norton's theorem. Okay? So you have your current source in parallel with your resistance. So this is another set work. So you have 2 circuits to do during your asynchronous class. Okay? And lastly, we have source conversions. Okay, so as you can see in Thevenin's, we have a voltage source in series with an internal resistance, and in Norton's, we have a current source in parallel with an internal resistance. In this one, we can have apply them as a source conversion, okay? Because there are circuits that are easily solved when we have voltage sources, and there are circuits that can easily be solved when we have current sources. So that means when you have a voltage source, you can convert them, okay, into a current source. So how do you do that? So we have here current divided by the resistance. That is the equivalent current source, okay? And then your RS here in series is just equal to your resistance here in parallel. So they are just equal. Or vice versa. If we have a current source, we can solve for for the voltage. What is voltage? Voltage is I times R. So the voltage here is equal to E I multiplied by RP. Okay, so how about here, the I here is equal to E divided by RS. So that is what we call source conversions. Usually, this is very easy when circuits that can easily be solved using voltage source are given with current sources or vice versa. Therefore, you can just convert them. Okay, so that is the relationship. That is how you are going to convert them. So, source transformation, voltage source to current source, we have to replace a voltage source Vs in series with a resistor R by a current source which is in parallel with the same resistor R. So, this is simply 100. This is simply 100 divided by 50. So, this is equivalent to 2 amperes. So, your IS here is equivalent to 2 amperes. And then, you just have to copy the value of the resistance. Okay? So, just divide 100 by R, Ohm's law. Voltage divided by resistance. So, that will give you the current source value that you have. And then, you just have to draw the resistance in series here. But this time, they are in parallel. And vice versa. So, current source to voltage source. If we wanted to replace a current source, IS, in parallel with a resistor by a voltage source, VS, what are you going to do? So, the current here, which is 2 amperes, and the resistance here, which is 50 amperes, will just get the voltage. So, the voltage is 2 amperes times 50 ohms, and that is 100 volts. So, the VS here is equivalent to 100 volts. And this parallel resistance here will just copy it, but this time they are connected in series. Okay, so 2 amperes in parallel with 50 is just the same or just equivalent to a 100 volts source in series with a 50 ohm resistor. Okay, so let's have an example. We have here use source transformation to determine VO. Okay, so we are going to convert this into a, so since we have a voltage source, let us convert that into a current source. So we are going to use this voltage in series. Okay, so we have here now the current source will become, so the current source will become 12 volts divided by 4. So this is 3 amperes. So this 3 amperes now, so this is our current. Okay, so that 3 amperes now, we will replace this in series, but this time we now have in parallel, and then we redraw the circuit. So this is your 8 ohms, and this is also our 8 ohms. So using current divider principle, this current here will divide between these 3 resistances. Okay, so what we wanted to know is the current across this 8 ohm resistor here. So what are we going to do? So let us solve for IO. So IO is equivalent to 3 amperes multiplied by, we have 1, the equivalent resistance. So we have 3 parallel resistances here. 1 over 1/4 plus 1 over 1/8 plus 1 over 1/8. Divide by 8. Okay, so divide by 8 because we wanted to solve for the voltage across this one. So that will give you 750 milliamperes. Okay, so the voltage output now is equivalent to the current, which is 750 milliamperes times 8 ohms. So VO is equivalent to 6 volts. So we convert this source into a current source. So we can easily use volt current divider principle. Okay, so let's have another example. Use source transformation to determine VO. So this time, we have a current source. So this is the current source in parallel with a resistance. So we convert that. So what is the equivalent voltage source for that? So the voltage source for that is simply 3 amperes times 4 ohms. or that is equivalent to 12 volts. So the 12 volts, this is our 12 volts. Okay, so this is your 12 volts in series, this time in series, so they are in parallel, so this time in series with 4 ohms. And then we just copy. So this is 2 and this is 8. Okay, like this one. So we have here, what is the voltage across 8 volts? So we will just make use of voltage divider. So if we use voltage divider, so the voltage across 8 ohms now is equal to the total source multiplied by 8, okay, divide by 4 plus 2 plus 8. So what is the answer? So this is approximately also equivalent to 6 volts. Okay, so that is from current source, we convert that into a voltage source. So this is very helpful. Okay, so this is very helpful, especially when you are solving problems that it can easily be solved using current source or using voltage source and vice versa. So you can make source transformation. From voltage source, you can transform that into a current source, or from current source, you can transform that into a voltage source. Okay, so these three topics are very related with each other. Therefore, you can easily understand them. Okay, so thank you very much for watching and have a nice day. Bye.